Hello, we're going to look at some integration by using substitution techniques. In our first example, we have the integral of x squared times 2x cubed minus 1 quantity to the fourth dx. On integration using substitution, which a lot of times what you'll do is you'll take the bulkiest part, which is usually in a set of parentheses or under a radical, and let a single variable replace that bulky part. For example, we'll let u equal 2x cubed minus 1. Take the derivative of u and you get 6x squared dx. Okay, so ideally what we're going to do is we're going to shrink this problem down. This will become u to the fourth. The rest of the problem, which was x squared dx, you can solve for that in your derivative line. If you divide both sides by 6, 1/6 du is equal to x squared dx. So x squared dx is replaced with 1/6 du. Nothing is lost, you just really trim it up. The antiderivative of u to the fourth is u to the fifth over 5 times 1/6. That gives us 1/30th u to the fifth, but put back in the original variable, so that makes 2x cubed minus 1 to the fifth plus our constant of integration. Second example, the integral of 5x times the cube root of 1 minus x squared dx. Again, a good idea is to start with the terms grouped either in parentheses or under a radical. In this case, we have a radical. So I'm going to let u be equal to 1 minus x squared. Taking the derivative of u will give us negative 2x dx. In this problem, we have a 5x dx. It's not a good match. So what I'm going to do is I'm going to take the 5 out. Since it's a scalar, it can be brought outside your integral. And now this x dx that remains, once you get the 5 out of there, you can solve by dividing both sides by negative 2. X dx can be replaced with negative 1/2 du. Negative 1/2 du. The cube root of our substitution is u to the 1/3. Remember the last video we discussed rational exponents. The antiderivative is going to be add 1, that's u to the 4/3, divide by your result, negative 5/2 times 3/4, u to the 4/3, but sub in the original variable, so that's 1 minus x squared to the 4/3. That gives us negative 15 over 8 times 1 minus x squared to the 4/3 plus our constant of integration. In this example, we're going to look at the integral where we have a radical in the denominator. Again, I'm going to take the bulky part, 1 plus x to the fourth, and I'm going to let u be equal to that. The derivative of u will be 4x cubed dx. In the original problem, we have x cubed dx. Solving for that, we get 1/4 du. X cubed dx can be replaced with 1/4 du. 1/4 du. Our radical being in the denominator, this is u to the 1/2, but when you move it up to the numerator, it's u to the negative 1/2. Any term that you go across the fraction bar, its power changes signs. So it's u to the positive half on bottom, but when it's moved up, it'll be u to the negative half. Take the antiderivative, add 1, you get a half, divide by the result. 1/4 times 2 over 1, square root of 1 plus x to the fourth, plus c, so that gives us 1/2 square root of 1 plus x to the fourth plus c. I want to do a couple of trig examples. Sometimes the angle is more than a single letter. Like this one, we have an angle of 6x. With trig, a lot of times the angle is going to be your substitution. So if I let u be equal to 6x, take the derivative, I get 6 dx. The only extra part in this problem, because we're going to substitute here, that's cosine of u, is that dx differential. Well, we can replace it with 1/6 du. The antiderivative of cosine u is sine u, so we have 1/6 sine u plus c. Remember to sub back in, and we have our final answer, 1/6 sine of 6x plus c. In the second example, we're going to take the same approach. Our angle is 1 over theta, and it's not always money in the bank to start there, but it's a great idea to start there. The idea is whatever you substitute, its derivative needs to be able to account for the rest of the problem. See, we've got 1 over theta squared d theta as the rest of the problem. This will be easily subbed out with a u, so it becomes cosine of u. Here's the issue. When you let u be equal 1 over theta, which is the same thing as theta to the negative 1 power, when you take the derivative, you get negative theta. Remember to subtract 1 from your power. That gives you negative theta to the negative 2. Cross that under the fraction bar, it's negative 1 over theta to the positive 2 d theta. The rest of the problem being 1 over theta squared d theta, well, that can be isolated, and that means you've made a good substitution. 1 over theta squared d theta can be replaced with negative du. Negative du. Now take the antiderivative. You get negative sine u plus c. Remember to put back in the original term you subbed out. It's time for it to tag back in. Negative sine of 1 over theta plus c. I wanted to do one or two that had exponentials, so I found one in the book that I liked. It was e to the sine pi x times cosine pi x dx. We're going to take the integral of that. When you have e built into your problems, most of the time the power of e will be your substitution. There's not an always to it, but that, again, I'm just trying to make suggestions. So bulky terms under radicals, groups of terms in parentheses, angles of trig functions. When it comes to e, maybe start with the power of e as your substitute. So I'm going to let u be equal to sine pi x. The derivative of that is going to be cosine pi x times pi, remember from chain rule. With trig, if your angle has a derivative other than 1, you chain it to the derivative overall. Now our problem, when we sub out, that's e to the u. The rest of the original problem is cosine pi x dx. We can isolate that by dividing both sides by pi. Cosine pi x dx can be replaced with 1 over pi du. E to the u has its own antiderivative, so that's 1 over pi e to the u, replacing u with sine pi x, and add your constant of integration. In the next example, we have 2x squared times the square root of x cubed plus 1. X cubed plus 1 is under a radical. Let's start with that. If we let u be x cubed plus 1, then u's derivative is 3x squared dx. This 2 is throwing it off a little bit. Our derivative line is 3x squared dx. If you don't get an exact match, that's fine. I'm going to go ahead and pull this 2 out, leaving x squared dx behind. Well, if we solve for x squared dx, that's 1/3 du. 1/3 du. With definite integrals, if you sub out, in other words, if you change from x to another variable, with definite integrals, your lower and upper limits have to be adjusted as well. In the substitution, when x is 2, u will be 2 cubed plus 1, which is 9. That becomes the new upper limit. The lower limit of 1, u equals 1 cubed plus 1, that's 2. That gives you the new lower limit. The good news with definite integrals is you don't have to change back out to the original variable. Once you substitute and change your integral limits, you can stay with that same substitution. So we have 2/3 out front. The antiderivative, add 1, that gives us 3/2. So u to the 3/2 divided by 3/2. Our new limits of 9 and 2 will sub in. So we have 2/3 times 2/3. Once that's flipped, that's 4/9. U to the 3/2, where we sub in a 9 and then a 2. That gives us 4/9 times 9 to the 3/2 minus 2 to the 3/2. So 4/9. 9 to the 3/2, that's square root of 9, which is 3, cubed, that's 27, minus square root of 2 is irrational, so I didn't change this one. You could write this as 2 square root of 2, but it really doesn't lead to a cancellation. If you did, then this would be your final answer when you distributed 4/9 to both terms. But you don't have to. This answer is actually good enough. Okay, so let's look at the integral from 0 to 4 of 1 over square root of 2x plus 1 dx. Remember, if you got a radical, start with the radicand, the material underneath it. Use that as your substitution. Most of the time, that's the right substitution. So if we let u be 2x plus 1, then the derivative of u is 2 dx. The original problem only has the differential dx, so if we solve for dx, that's 1/2 du. Remember, with a definite integral, we started with 0 and 4. That's attached to x. Since we're subbing out with a u, we have to translate those. 2 times 4 plus 1 gives us 9 as the new upper limit. 2 times 0 plus 1 is 1. That's our new lower limit. Because this substitution was u to the half in the denominator, when it's moved up, it becomes u to the negative half. Take the antiderivative, add 1, that brings you to positive half, divided by the result. 1/2 times, flip it, 2 over 1, and then sub in 9 and 1 in for u. These cancel. Half of 2 is 1. Square root of 9 to the first power is 3. Square root of 1 to the first power is 1. 3 minus 1 is 2. And then finally, I wanted to do an example of a definite integral where we had an exponential term. Remember, with an exponential term, excuse me, a good substitution, if it's required, will be the power. So we're going to let u be x squared. Derivative of u will be 2x dx. 4x you can write as 2 times 2x. So what I did here was I took this 4 and I brought 2 of it out and I left 2 of it in. So that 2 times 2 is still 4. But the reason I did it that way is our derivative line, 2x dx, is made up right here. All right. So we have 2 times e to the u, remember that was our substitution, 2x dx, that's our du. Don't forget to change your upper and lowers. Our substitution is u equals x squared. U equals 4 squared makes 16. U equals 3 squared equals 9. And I put that over here in the brackets for you to check out. Put the original upper and lowers through the substitution to get your new upper and lower limits. The antiderivative of e to the u is still e to the u times our 2 out front, and we're going to sub in a 16 and a 9. So that's 2 times e to the 16 minus e to the 9. These are irrational, so you don't have to worry about simplifying any farther. Let me know if you have any questions or concerns. Reach me by email or phone, come by the office, or ask in class. And I hope this video helps.